We're fine. Okay. So are you all able to hear us? Oh, but they can't respond. Inez, is this fine? Okay, good. Yeah, that's fine. Okay.
Good morning. My name is Sarah Hustis, and I worked on a project concerning managed lanes on arterial roads. I worked on the project alongside another intern, Andrew Fell. And so we split up the presentation. I'll be doing the introduction and then covering high occupancy toll lanes, and then Andrew will cover the other portion of the presentation. So first I'm going to go through what are managed lanes, then go through the project description, including objectives and task breakdown. Then I'm going to be speaking about high occupancy toll lanes, giving a general definition as well, going over some characteristics. Then I'll be going over some examples of high occupancy toll lanes. Then I'll be speaking about project planning, implementation, and monitoring. And then at the end, I have a summary and some references as well. So what are managed lanes? As many of you may know, the Federal Highway Association defines managed lanes as a set of lanes where operational strategies are proactively implemented and managed in response to changing conditions. These operational strategies include some management tools such as pricing, eligibility, and access. So basically the way to set up a managed lane is to either price the lane, restrict the lane's eligibility, or restrict the lane's access. And depending on the combination of tools you use is the type of managed lane you get. These types include HOV facilities, bus-only facilities, bus toll facilities, high occupancy toll facilities, truck-only toll facilities, and express toll facilities. And as you can kind of see here, the HOV lanes, for example, restrict vehicle eligibility, where pricing and eligibility restrictions would result in HOT lanes, or high occupancy toll lanes. So the project description, the project was commissioned by the Florida Department of Transportation. The title of the project is Deployment Strategies of Managed Lanes on Arterials. The project PI was Dr. Yin, who Andrew worked with, and the co-PI was Dr. LaFontaine, who I worked closely with. The project objective, as you can see on the slide, was to examine managed lane deployment strategies on arterial roads, to identify tools to evaluate their performances, and to investigate ways to coordinate the deployment of managed lanes and their operation. There were 5 basic tasks. One was to review the state and national practices of managed lanes on arterials. At that point, when the task was completed, we were to send in a literature review. Then the second task was to identify and select managed lane strategies. The third task, which was closely related to the second, was the implementation and monitoring program. Task 4 was the identification of evaluation tools, and task 5 was managed lanes on limited access facilities and arterials. After these tasks are completed, which they have not quite been, there will be meetings and then a final report. I primarily worked on task 1 by evaluating the literature available on the subject. So, like said, our project had a greater scope than just high occupancy toll lanes, but because Andrew and I both worked on the project, he's going to be speaking about 2 other types of managed lanes that are applicable on arterial roads, while I'll be talking about high occupancy toll lanes. So first, to define high occupancy toll lanes. Toll lanes are high occupancy toll lanes, are lanes to which high occupancy vehicles have access for either free or a reduced charge, where single or low occupancy vehicles may purchase access to these lanes for a fee. So the potential objectives when beginning a high occupancy toll lane project are split into several categories. First of all, mobility and reliability improvements, such as travel time savings, reduced travel time variability, and goals such as that. You can also have some traffic volume goals in that objective. Environmental improvement might also be an objective. So, for example, to reduce the amount of air pollutants or better air quality. Safety improvements can also be a goal with, for example, a reduced number or severity of safety incidents. There are several conditions favorable to successful implementation of high occupancy toll lanes. The two main ones are high density corridors in metropolitan areas with limited travel options, and the other are underperforming HOV lanes. And the underperforming HOV lanes can either be underutilized, in which case converting them, the existing lanes to HOT lanes can increase their performance by increasing traffic volumes on the lanes, or they can be underperforming in that there's too much demand for the HOV lane itself, in which case you might add another lane, but the HOV demand itself might not warrant the other lane, so adding a lane and converting both to HOT lanes is a potential option in that case. So here's an overview of HOT lanes in the United States. As you can see, the first one was I-15 in San Diego, California. It was opened in 1998. It has 4 lanes, and the 2 outer lanes are both in one direction, and then the inner lanes can be reversed. So you can have either a 2-lane per direction configuration or a 3-lane in one direction and 1 lane in the next configuration. These are 20 miles long. They're separated by movable barriers, which makes sense since you can alter the lane configuration. There are many access points in each direction. The occupancy requirement is HOT2+, so you count as a high occupancy vehicle starting at 2 occupants in your vehicle. And only single occupancy vehicles pay a toll. And the operation is 24/7. You can see many more HOT lane projects here. Another one to point out is I-95 in Miami, Florida, of interest because our project was commissioned by the Florida Department of Transportation. This was opened in 2008. It has 2 lanes per direction. It's 7 miles long. The separation is through flexible pylons. There are 3 access points northbound and 5 access points southbound. The occupancy requirement is HOT3+, so you're considered a high occupancy vehicle at 3 or more occupants. And these high occupancy vehicles do not pay a toll, while others do. And the hours, there are toll hours, or no, this one is also 24/7, excuse me. Here are some more HOT lanes, so please take a look. I'd like to point out that the Fairfax County, Virginia lanes were opened as recently as November 2012, which I found to be interesting. They have 2 lanes in each direction, 14 miles long. They're separated by posts. There are 11 access points in each direction. Again, an HOT3+ occupancy requirement, and again, 24/7 operation, and only the low occupancy vehicles or those not meeting the HOT3+ will pay the toll. So if you notice, the previous HOT lane experience, which was summarized in the last 2 slides, has only been on highways and freeways. And there are several characteristics of arterials that do differ from highways or freeways that would change the implementation of HOT projects on arterials versus the past experience with highways. Some of these characteristics include that you can access local streets and businesses from arterial roads, which is not the case in freeways. The speed limits on arterials tend to be lower than on highways, usually in the range of 35 to 50 miles per hour. There are also intersections on arterials that can be signalized with traffic lights or just signed. There's also frequent stopping due to passenger loading and unloading or deliveries to local businesses or other situations such as bus stops. And due to this frequent stopping and other factors, there's also large differences in speed between the different vehicles on the arterials. So the things I'm going to go through next were all referring to the literature available, which is all on highway implementation. And then at the end, I'm going to tie in how does the relevant highway experience relate to arterials. So the HOT lane project planning process is split into pre-planning and planning. The pre-planning includes identifying that a need exists or a problem. So for example, identifying that an HOV lane is underperforming, and then considering solutions. And HOT lanes should be considered in solutions where appropriate problems arise. The planning process is then split up into identifying constraints, choosing preferred methods, and publicizing a project. The constraints can be physical, institutional, having to do with public acceptance, or operational. A big barrier that can be institutional is, for example, who owns the project, who will operate the project, tolling strategies to choose, and things like that, which I'll discuss a little bit later. Preferred methods include methods for tolling, so electronic toll collection versus manual toll collection, whether or not to have transponders or do video tolling. The institutional structure, like said, choosing who owns and who operates the facility, who does the enforcement for the facility, etc. And financing. Financing is available through traditional methods such as fuel taxes, but also through federal grants or special transportation project grants. Publicizing the project was emphasized in the literature as one of the most important aspects of the project due to public opposition in many cases or equity concerns. So beginning to publicize the project as early as possible and showing it in the most beneficial light is very important. This can be done through a political champion both at local and state levels, marketing efforts, and focus groups, stakeholder groups, and that sort of stakeholder, I guess, association. The implementation of high-occupancy toll lane projects includes the design, procurement, and construction and operation steps. Some design concerns that will arise during the project are what is the occupancy requirement? So is it HOT 2+, where a 2 or more person vehicle is considered a high occupancy vehicle and exempt from the toll, or is it going to be 3+? How is the toll structured and how will the toll be collected? The tolling structure can be a set structure, so a set schedule of fees that may or may not change during the day, or you can use dynamic tolling, so that's a real-time update in tolling. The San Diego facilities, I believe, update their tolls every 6 minutes to reflect changing traffic conditions. Markings and signage is also an issue because the people in the area may not be familiar with the concept of an HOT lane. So these markings and signage have to be very clear in order to prevent any operational problems. And then the type of separation is also important because there are very different ways you can go about separating an HOT lane. For example, you can put in a concrete barrier, which is the most separated, or you can have any sort of varied separation down to just painted lines. The procurement and construction phase is selecting a contractor or concessionaire, if applicable, obviously, and then obviously the construction of the facility. Once the facility is in operation, there are several different things to worry about. The accounting, because the tolls do obviously generate revenues, maintenance of the facility, customer service, and then enforcement is a big issue because of the way the high occupancy tolling is configured. Since high occupancy vehicles will pay either no toll or a reduced toll, it's important to enforce and verify the occupancy of a vehicle when conducting enforcement activities, which has proven to be a challenge in many cases. Performance monitoring is also an issue, which I will get to at a later point, namely now. Right, so several things about performance measures. Performance measures should reflect the objectives set for the project early on. So for example, if the objective of the project was to increase the capacity of the roads, a performance measure should be the traffic volume. Other performance measures can include average lane speeds, travel times, the variance of both, traffic volumes, as I mentioned, customer perceptions, compliance rates, incident data, how many pollutants are in the air, and there may have been revenue goals set. So revenue is also an important performance measure for HOT lane projects. Data can be collected several ways. There can be continuously and automatically collected data, which is especially feasible when there's video tolling in place and things like that. There can also be manual sample data for special kinds of performance measures. And then customer and agency surveys are also important when measuring customer perceptions. So here's an example of a performance monitoring type situation. I chose the SR 167 in Seattle. So the average lane speeds they compared them to the previous operations, which were HOV operations. The average lane speed was unchanged at around the speed limit. The volumes had increased by 15%. The general purpose lanes that were adjacent to the HOT facility had an average speed increase of 8%. The general purpose lane volume increased by about 4 to 5%, and the average time savings for the HOT customers were about 9 minutes during the morning peak period and 6 minutes during the PM peak period. Customer perceptions overall were very good, with 88% of respondents saying they use the lanes to avoid congestion and make a faster trip. And then 70% of them said they were likely to use D lanes again. The compliance rate was very high at 95 to 97%. In terms of safety, there was a 4% reduction in traffic incidents compared to the previous HOV operations. And as to revenue, there were 3,300 tolls tripped per weekday, which was a 50% annual increase and an 87% increase versus 2 years prior. And there was a revenue of $750,000, which was a 35% annual increase. So in the report I read on this, they considered this a successful implementation that met their goals as measured by the performance measures up on the slide. So then, applying managed lanes concepts to arterials. As I mentioned earlier, the HOT lane projects that have been implemented in the past have been implemented on highways and freeways, but they may also be feasible on arterials. And a consideration is the more like a freeway and arterial is, the more feasible implementation. And that's because of the characteristics that I mentioned earlier with the stopping and the intersections. And ways that you can make a freeway or an arterial more like a freeway is by limiting either turns or access. So eliminating intersections, basically, because turning causes delays, and access of vehicles either turning on or off the arterial do cause delays that make an arterial more like an arterial and less like a freeway. And there's also the possibility of adding queue jumps, which is a way to avoid intersections. There are several different ways to avoid intersections. Some are like transit signal priority, where the light will change, for example, for buses and situations like that, or physical queue jumps, where you can, for example, pay to cross a bridge over the intersection instead of going through the intersection. And they could be used on arterials to improve the mobility by reducing the number of intersections that HOT lanes face, which would make them more feasible. And then other types of managed lanes concepts that are used on arterials, which Andrew will be talking about shortly, are HOV lanes, or high occupancy vehicle lanes, and bus only lanes. So to summarize, the project I worked on was commissioned by the Florida Department of Transportation and concerned strategies of managed lanes on arterials. But to date, the high occupancy tolling implementation has occurred only on freeways and highways. Key issues with high occupancy toll lanes are the roles and responsibilities of various agencies, including, for example, municipal planning organizations or state departments of transportation, public support, financing, design, enforcement, and performance monitoring. And then the potential for arterial implementation of HOT projects. The more freeway-like an arterial is, the more applicable previous experience. And two ways to make arterials more freeway-like are turn and access restrictions and queue jumps. And then I have also provided some references. So feel free to look at those at your leisure. That was it.
Quick questions or any clarification?
So, do you know how to enforce the HOV lanes? I mean, for HOV lanes, it's easy to see if the vehicles are single occupancy or one occupancy.
Yes. The way to do it for...
Sir, can you repeat the question?
Yes. So the question was how to implement HOT or implement enforcement in HOT lanes, because for HOV lanes it's easier to see if the vehicle is single occupancy or more. And the answer is there has to be a similar manual enforcement there has to be kind of a joint effort between various police agencies, for example, the Highway Patrol, in the case of highways, and the local police enforcement. And it's very similar, actually. They have enforcement areas where police officers will sit and visually verify the occupancy. In some cases, they also make high occupancy vehicles have a transponder as well, and then they can turn it off or on depending on the facility and whether or not they're carpooling or not. And then there are like scanners that the police vehicles have that can see if the transponder is on or off. So they'll visually verify, for example, like this person is a single occupancy vehicle and has the transponder off, and then they can pull them aside to an enforcement area that's designated and has to be part of the design of the facility, and then they'll pull them over and assess a violation.
So there's no automated occupancy recognition.
Okay, the question was, so there's no automated occupancy verification, and the technology exists in some situations, but there are various legal concerns in terms of privacy concerns, and also sometimes the technology isn't is more or less reliable depending on the conditions outside. Also, a lot of the research I was reading about the enforcement is people respond better to enforcement that's very visible, so they would respond better to seeing a police officer pull someone over versus getting a ticket in the mail.
That's one question. So in the literature, did you see any instances that they implement the hot lane without having HOV lane, which has been underutilized and then converted into hot lane?
The question was whether or not there were HOT lane projects that weren't previously an HOV lane project.
So I guess it's usually like that there's HOV lane that's underutilized, and then they convert it to hot
Yes.
lane.
So a lot of the projects do use HOV lanes that are underutilized, because that's a very good situation for a hot lane to be successful. However, there are projects, I believe the 495 Expressway in Virginia was a completely new, they just built it as a hot lane facility. So that is possible, but it's more common due to cost constraints and other things to convert HOV lanes to HOT lanes. Okay. Does I don't know. Okay, I can't see anyone online. Okay, I hope not.
Good morning, everyone. I'm Andrew Fell, and I will also be presenting on the applications of managed lanes on arterials. Sarah presented on high occupancy toll lanes, and now I will be presenting on high occupancy vehicle lanes and bus-only lanes. First, a reminder of what managed lanes are. These are lanes that use various operating strategies to meet performance targets, usually a certain level of service. Things that might be used are pricing, vehicle eligibility, or access control. And these kinds of lanes, they include express toll lanes, HOV lanes, truck-only lanes, reversible lanes. For my particular research, I focused on HOV lanes and bus-only lanes. Specifically, I was looking at the application on arterial roads. What I did was I examined the existing guidelines for arterial managed lanes. I also looked at the current applications of these managed lanes on arterials. And then using the various case studies, I looked to see what lessons could be learned from them and use those to redefine the guidelines. So I'll begin with HOV lanes. High occupancy vehicle lanes are restricted to vehicles carrying a certain minimum number of occupants. Usually this is either designated as 2+, 2 or more occupants, or 3+, 3 or more occupants. They may also be open to buses, motorcycles, and low-emission vehicles, depending on the facility. They are more common on freeways than on arterials. It was kind of hard to find instances where HOV lanes were on arterials, since they are much more common on freeways. HOV lanes have various objectives. The main ones, though, are to increase the person moving capacity of the roadway without having to add more lanes. This is done by increasing the average number of people per vehicle, since HOV lanes give an incentive for people to carpool. They provide travel time savings and travel time reliability to HOVs, and this encourages the formation of carpools and van pools. You may be wondering why we would want to implement HOV lanes. Basically, Traffic volumes in this country are growing at a very fast rate, much faster than the infrastructure can be expanded to keep up with them. The available right-of-way, that is the land available for new lanes, is very limited or non-existent, especially for arterials, since the development around limits the land that can be used for expanding roads. HOV lanes present a very cost-effective means of increasing roadway capacity, since oftentimes lanes don't have to be added, and the lanes that use high-occupancy vehicles can carry more people than general-purpose lanes. A basic rundown of the various advantages and disadvantages of HOV lanes on arterials. Advantages are HOV lanes have relatively low operating costs. They're easy to implement or convert back to general use if they don't work out, since you don't have to add another lane for an HOV lane, but oftentimes new lanes are added just for the purposes of carrying HOV lanes. So if the HOV lane is regarded as a failure, it can be easily converted to a general purpose lane. They can carry more people than general purpose lanes. They reduce the travel times for high occupancy vehicles, and they might also improve the air quality along the roads. That's somewhat debatable, but it is one major reason for implementing HOV lanes. HOV lanes also have a number of drawbacks when applied to arterials. The delays in the general use lanes may increase. This primarily would only happen if a lane was taken from an existing road and converted to high occupancy vehicle only use. Then there would be fewer lanes for mixed flow traffic, and congestion would increase. The public may perceive HOV lanes as underutilized. If there aren't as many vehicles in the HOV lane as the general use lanes, it might be regarded as a waste. It can be difficult to enforce the occupancy restrictions. It's not always easy to tell if there are 2 or more people in a vehicle. Oftentimes, the on-street parking in arterial areas may need to be removed in order to make way for the HOV lane. And also, adding HOV lanes may require that there be turn restrictions at intersections, since oftentimes HOV lanes are added to the right lane, and right-turning vehicles would also have to use the right lane, so hence the need for turn restrictions. Now, situations where HOV lanes might be warranted are in places where geographic barriers like mountain ranges and existing developments concentrate travel patterns and constrict traffic flow. One major example is in California, due to the geography there, with the mountains and forests. They constrict travel. They constrict travel to just a few corridors, and these corridors are often very crowded. Also, HOV lanes might be useful when there is congestion in the general purpose lanes. The guidelines for just when an arterial is congestion enough for this really don't exist in literature, but for freeways, level of service speed or speeds consistently below 35 miles per hour are regarded as a good conditions for possibly adding HOV lanes. Also, if there are limited resources, funding, or available right-of-way to expand the road, it might be better to make either convert existing lanes to HOV use, or to add new lanes but make them HOV lanes so that more use can be made out of them. Guidelines for HOV lanes. Most of the existing guidelines are for freeways, but these can also be adjusted for use on arterials. Performance guidelines are travel time savings of ideally 1 minute per mile, but it should be at least half a minute per mile. That's for freeways. For arterials, often the travel time savings are about half a minute per mile. Overall, the travel time savings should be about 7.5 minutes, but at least 5 minutes, so that it makes a noticeable difference for travelers. According to the American Association of State Highway and Transportation Officials, arterial HOV lanes should carry at least 200 vehicles per hour per lane, although that figure is just a general guideline. All these guidelines actually may vary by project, and they depend on the general lane congestion and on the local conditions and perceptions of the areas where they're implemented in. Areas that have more experience with HOV lanes will be more tolerant of a lower number of vehicles per lane than in an area where they're being added for the first time. One case study of making guidelines for arterial HOV lanes is in Santa Clara, California. When they set out to evaluate their arterial HOV lanes, they adapted existing guidelines used for freeways. And these are the guidelines they came up with. And these guidelines would be specific to the Santa Clara County area. HOV lanes should carry at least 400 vehicles per peak hour, and at least 880 persons per peak hour. They considered that these HOV lanes should have a lane productivity of at least 0.8, and by lane productivity, that is the ratio of HOV lane users to mixed flow lane users. The HOV lane should have a violation rate of no more than 15%, and there should be travel time savings relative to the mixed flow lanes. Yes.
So the user, the productivity, the user needs personal or people?
That would be occupants, as in people, users. After reviewing the existing guidelines, I looked at some case studies. These included the Montague Expressway in Santa Clara, California, also the South Dixie Highway in Miami, and Santa Fe Drive in Denver, Colorado. So first, the Montague Expressway, this was implemented in the 1980s. 20 years later, the County of Santa Clara evaluated the performance of various arterial HOV lanes in the area, including the Montague Expressway. And what they found was that users of the HOV lane actually lost time compared to users of the general mixed flow lanes. The HOV lanes had high violation rates in some areas as high as 60% due to the lack of access control. Especially at intersections, vehicles would cut over into the HOV lanes to turn right, and also vehicles coming out of driveways, for instance, might inadvertently use the HOV lanes. The HOV lanes were underused while the rest of the road operated at level of service F. And level of service F is the lowest performance of a road, referring to frequent congestion and low travel speeds. Ultimately, it was decided to convert the HOV lane to general use. It was also decided that the road should be widened and the added lane should be used as an HOV lane on a trial basis to see if HOV lanes could still be made to work if the road was a little less congested. Next is the South Dixie Highway. This was one of the first applications of HOV lanes on arterials. It was implemented in 1974. Evaluations of this road found that vehicles using the HOV lane experienced travel time savings of 5 to 10 minutes. The HOV lanes carried 40% of the total volume of people that moved on the road. Vehicles in the HOV lanes moved 7 miles per hour faster than vehicles in the general use lanes. They also found that the accident rate increased after the HOV lanes were implemented. This was due to the placement of the HOV lanes next to a contraflow bus lane, and also due to the HOV lanes being narrower than the standard lane width. This HOV lane was closed by 1985. Even though it was performing well, it might have been closed to make way for a local express train route. Next is Santa Fe Drive in Denver, Colorado. It was implemented in the 1980s and is still around today. A recent evaluation of this facility found that at the time the facility was implemented, there were virtually no existing design standards for arterial roads, both at the state and national level. But even today, there is a lack of design standards at the Colorado Department of Transportation, and these make it difficult to enforce and evaluate the facility. Unlike many HOV lane facilities, this HOV lane is in the left lane. This makes it hard to maintain the lane since it prevents it makes it difficult for other traffic. Enforcement of the facility is uneven across the various jurisdictions that it passes through. From these particular case studies, we can take a few lessons from these. Things that should be avoided are close spacing of intersections. Intersections interrupt the flow of high occupancy vehicle lanes, so turn restrictions might be needed. The Montague Expressway in California was placed parallel to a freeway HOV lane, which undermined its usefulness. So placement next to a HOV lane on a freeway might not be a good idea. HOV lanes should not be shared with high volumes of buses or right-turning vehicles, since this will undermine the travel time savings for HOV lanes. HOV lanes should be supported by the State Department of Transportation with design guidelines and regulations. And the enforcement should be consistent across the various places where it occurs. Now there are various computer simulations and tools for evaluating HOV lanes, both before they're added and after they're implemented. Among these are Quick HOV. This is a a demand estimation tool used to estimate how much demand HOV lanes will receive. In case studies that I looked at, it tended to underestimate the HOV lane use and overestimate the number of HOVs using the general traffic lanes. Another demand estimation technique is the modified Charles Rivers Associates model. This model more closely estimated the number of HOV lanes using the managed lanes, but it did not estimate the volume of HOV traffic using the general use lanes. And finally, there's a program called Smart HOV, which is used to estimate the travel time savings from HOV lanes. Case studies I looked at showed that it may substantially overestimate the time saved from using the HOV lanes, particularly in cases where buses also use the lanes. So this particular program needs refinement and further enhancements. Next, I'll go to bus-only lanes. These are more commonly seen on arterial roads than HOV lanes are, particularly in crowded city districts. As the name implies, they are restricted to buses, and they are most often found in urban areas with heavy bus traffic. The goals of bus-only lanes are to provide travel time savings and travel time reliability for buses, and also to increase the usefulness of buses, increase bus ridership. The advantages of bus-only lanes are that they reduce bus travel times, they improve bus travel time reliability, so how often buses arrive on time. They're relatively inexpensive to operate and easy to enforce. On the other hand, delays in the general use lanes might increase due to the presence of bus traffic. The public might perceive the lanes as underused and therefore demand that they be converted to general use. And also, on-street parking may need to be removed to make way for the bus-only lane. Pre-existing conditions for adding bus-only lanes. The exact volume of bus traffic needed is variable and varies depending on the guidelines you look at and the particular location being looked at. But it should be at the very least 25 to 30 buses per peak hour. And also buses should be experiencing delays due to mixed flow traffic. According to AASHTO, bus-only lanes should carry at least 50 buses per hour per lane, but again, that number is variable. And on a different type of bus lane called a bus mall, a street which only carries buses, there should be at least 80 buses per peak hour per lane. A couple of case studies I looked at and which I thought were especially useful are Spring Street in Los Angeles and Madison Avenue in New York. Spring Street has a contraflow bus-only lane implemented in the 1980s. An evaluation of the road found that bus speeds increased by about 15% on both Spring Street and Main Street after the bus lane was implemented. Other vehicle traffic also benefited with their speeds being increased by 20 to 40%. And this lane is still around, to the best of my knowledge, a relatively successful bus-only lane. On the other hand, Madison Avenue in New York has not been as successful. It was implemented in 1981. Initially, buses experienced travel time savings of 5 to 6 minutes, and buses had better travel time reliability and bus ridership increased. 20 years later, an evaluation of bus lane found that bus speed was still only about 6.5 miles per hour due to the bus lanes often being blocked by general use traffic. Currently, options are being explored for improving bus transit in New York City. From these and other case studies which I looked at, there are a few things that should be avoided when implementing bus-only lanes. Bus lanes should not be blocked by general traffic, so a good level of enforcement should be used. And also, and this applies to bus malls in particular, since they often serve a sort of beautifying function for a city. The design may be aesthetic, but it should not detract from the durability of the facility. One case where involving a bus mall where the pavement doesn't last very well is in Denver, Colorado. 16th Street Bus Mall is made of granite pavers. They look very pretty, but the heavy bus use wears them down, as you can see in this picture. The top part is the sidewalk, and the bottom part is bus lane. And so you can see that the granite gets worn out very quickly and requires costly maintenance. So to summarize, I studied managed lanes for arterials and bus lanes and HOV lanes in particular. Unlike freeways, arterial HOV lanes are relatively uncommon, and those that in those instances that I could find were very old, often dating from the 1970s or 1980s, and some of them no longer are in existence. Reasons for there being so few arterial HOV lanes are there are fewer access restrictions on the arterials, so they're harder to enforce. There's limited right of way, and again, it's hard to enforce. Arterial HOV lanes provide benefits for high occupancy vehicles in the form of improved travel time and increase the person moving capacity of the road. But on the other hand, they require a public outreach campaign by the Department of Transportation or whatever agency is implementing the HOV lane. They require substantial enforcement, and the existing traffic patterns may need to be adjusted to make way for the HOV lane. Bus-only lanes, unlike HOV lanes, are more common on arterials, especially in major urban centers. Bus lanes provide travel time savings and travel time reliability for buses, but they require enough bus traffic to justify their existence, and also on-street parking and loading and unloading areas may need to be cleared to make way for these bus lanes. So in light of all that I've said, a lot of work needs to be done regarding managed lanes on arterials. First of all, a screening process for selecting the appropriate type of managed lane on a road needs to be developed. So whether it should be an HOV lane, a bus lane, or even an HOT lane, there needs to be some process for determining which kind of strategy to use. A framework for evaluating managed lanes on arterials needs to be developed. So how do we know when a managed lane is performing at the set objectives? Also, practical measures of effectiveness need to be defined. As in travel time savings or number of HOVs using an HOV lane or violation rate. and also methods of evaluating and forecasting these measures need to be developed. So both before and after the managed lanes are implemented, there needs to be some sort of tool or strategy for determining whether these managed lanes will get enough use and whether they're warranted. That's all that I have for my presentation.
I just have some clarification questions. On the bus lane on the two street, are those streets one-way street?
The question was, is a bus street a one-way only street? From the cases that I looked at, bus streets are often two-way, lanes going in one way and lanes going in another direction. Although it's certainly possible for a bus street to only be one way.
Okay, I'm thinking about specifically on the Spring Street, for
Spring
example.
Street, yes.
Was that a one-way street? Because we talked about the bus lane being conflict flow. It looks like in the picture that it's one way, but I wasn't sure.
The question was, is Spring Street, are the bus lanes on Spring Street only one way?
No, I mean, the Spring Street, one-way street for the general purpose.
For general purpose, I believe it is actually one way, and then the buses go the other way.
What about the one in New York City?
So you said the street is one way for general purpose, and then with the bus only lanes,
Yes.
two ways. Bus only lane. You said it's control flow, which means that reverse direction.
Right, that's right.
Two-way or one-way?
One.
And what about New York City, the one in Madison?
Yes.
Is that the same situation?
Madison Avenue, I don't believe that's the same situation. I believe that's two-way, yes.
This one.
Any other questions? The question was, do managed lanes on arterials have dedicated enforcement areas? As far as I know, they generally, oftentimes they don't, although certainly it's a good idea for there to be areas set aside for enforcement. And one of the guidelines I looked at, having a designated area for enforcement was one of the suggested guidelines. But to my knowledge, that is not often implemented in practice.
Is there a way to minimize this? Is there a way to minimize this off the screen?
It should.
Well, if you do your slideshow, hopefully that doesn't show. It shows. Okay.
Yes, that's all right. If those of you online can't hear me or need to stop me at any point, that's completely fine. But to start, my name is Corey Dorman, and I work very closely with Dr. Siva Srinivasan on a project entitled Crash Prediction Model Methods for Freeway Facilities with Managed Lanes. And my focus was on safety as opposed to operation and performance. So we're kind of looking at crash distributions and crash frequency and things along the line of purely safety. So just a brief overview. First, I'm going to go through the background of the situation, kind of what the project's all about, then the purpose, why we're doing this, and literature review and the compilation of existing facilities is what I specifically worked on for this project, and kind of what I contributed to the research project as a whole. And then I delved into a case study, specifically with I-95 Express in Miami, Florida, and everything that ensues after that is just kind of the software and the data analysis and the findings that I found with the data that I analyzed specifically for the express lanes in Miami. And then I'll go over all the dimensions that I analyzed and show you some graphs and charts. And then I'll go through my findings and analysis, and finally a summary to really tie it all together and some conclusions that I found. So the background. This is an FDOT-funded project, like the two previous presenters. It was also for them as well. And reason being, managed lane facilities are an ever-growing facility and an option for designers and planners of these roadways. And so the FDOT is certainly interested in getting a better picture and a better idea of how these facilities function, how they, specifically on the safety perspective, so they can better plan and design these facilities. And there are currently 345 HOV lanes in the United States and 13 HOT lanes. The HOT are a bit newer, but they're definitely growing, and they're becoming a new useful tool. And currently also, the FDOT is interested because as of now, the status quo is there is no current framework or current standardized prediction method for crashes on these facilities. A report was published in May 2012, which will make its way into the Highway Safety Manual, that does cover freeway facilities and their interchanges, but not specifically with managed lanes. And because this is growing and becoming so important, this is why this research is kind of being undertaken. And so that brings us to the purpose. So what we're trying to do here is develop crash prediction methods and models and equations that we can ultimately publish into the Highway Safety Manual, along with the equations that already exist there that have to do with highways on urban and rural arterials. So we'd like to add freeways with managed lanes into this as well. And like the ones already published in the Highway Safety Manual, our crash prediction model is going to involve a safety performance function, crash modification factors, and of course a local calibration factor. So my first task was literature review. So ultimately what this ended up being was that I reviewed all of the current literature that had to do with freeways, managed lanes as it pertained to safety. I used a US library system to find all these articles, and there were quite a bit. There were also a lot about operation and performance. There was a far more wealth of that information than there was for safety. And the ones that did have to do with safety really suggested that safety was neither degraded nor improved. And what they did in these reports is they compared facilities with managed lanes on a characteristic-to-characteristic basis. And they would purely analyze the crash differences and the frequencies for facilities that, say, had a physical barrier from the managed lanes and general purpose lanes, and perhaps just a buffer-separated barrier. And so they would just compare the crash frequencies between those two and compare them. And what we want is kind of a more general perspective of, regardless of what characteristic these freeway facilities have with managed lanes, we want to be able to predict the crashes on them, regardless of what characteristics they have. And so ultimately, all the research that I found and read was just saying that a lot more research was needed and to make anything conclusive. My next task with the project was a compilation of existing facilities. The purpose of this was really just as a good tool to compare all the different HOV and HRT facilities that currently exist. Like I said, there were 345 HOV and 13 HOT. So this is hopefully going to become a helpful spreadsheet in which we can compare all the different characteristics that are so variable and unique to each facility, and be able to integrate this into our equations and be able to develop accurate equations and have these characteristics as being essentially inputs and variables in this equation, where you more or less just are plugging and chugging these characteristics, and you get an output of a safety that can be actually quantified in a crash frequency per year. So then I went ahead and I delved into a specific case study. And the case study was in I-95 Express in Miami. From Miami, I chose it. Doesn't mean I like the road any more than you do, but basically this seemed like a really good idea because it's a fairly new facility, a newly converted facility. And as you can see in the illustration, the construction was divided into really three parts. Phase 1A, which is highlighted in yellow, was just the northbound express lane. This was it used to be only one HOV lane in each direction, and this was now converted into 2 express lanes in each direction. And that led to narrowing the general purpose lanes since there was no additional right-of-way and there was no additional pavement constructed at all. But the yellow, the first phase, was purely northbound. And then the orange, which is phase 1B, was purely southbound and added a small part to the northbound express lanes as well between Interstate 195 and 395. And then phase 2 was the entire north part, north of the Golden Glades interchange area. And this is both northbound and southbound. However, the area that I analyzed in particular, the segment I analyzed, was purely the Golden Glades interchange area all the way down to Interstate 395. So phase 2 is not covered simply because it's currently under construction, and I wanted to be able to look at a segment that before construction had even happened, during construction, and then at least a year or two of this segment actually under operation. So like I said, it was a recently converted HOV facility, and these are kind of just the characteristics. And so the first tool that I used to analyze the data with I-95 Express was Signal 4 Analytics. And this is a very powerful, useful tool. It's web-based. And what I was able to do is really just zoom into the exact segment that was in question and highlight exactly which lanes that I wanted to look at and extract all the crash records from whatever period I wanted. So my period was 2006 to 2012, which, like I said, covered before construction as an operating HOV facility, during construction, and then post-construction. So there's a very useful tool with Signal 4 Analytics, which enabled me to actually export all the crash records from 2006 to 2012 into a simple, easy-to-use spreadsheet where further analysis could be conducted. So speaking of further analysis, then I was able to use IBM's SPSS software to export these crash records from Signal 4 and then analyze them further. Again, this is a very powerful tool that enabled me to do with relative ease some really good analysis and draw up some good cross tabulations and charts. And it was very useful in trying to identify trends and anything of note that happened in this particular case. So these are the dimensions that I analyzed using SPSS. The ones that are asterisked I don't really go into for brevity's sake, but also because they really didn't show anything of note. A lot of the crashes, for example, during the weather condition, happened in clear conditions. Over 60% did. There was nothing shocking here. And with the lighting condition, this is I-95 in Miami. The lighting was more than sufficient. So this wasn't an issue, and I didn't feel needed to really necessarily be presented. But as far as total crashes and breaking down these total crashes into their crash directions, northbound and southbound, and then crash type, whether that be rear end, side swipe, or anything else, I found that that was probably more interesting to present and would have more things of note. So this was kind of the first chart that I'd like to present, and this is kind of the most zoomed out picture on a yearly aggregate basis. And though when you zoom out, trends might become more apparently obvious, I also realized that you might neglect some micro trends, things happening perhaps on a monthly basis or even on a seasonal basis. But this is the most zoomed out picture that I wanted to present first. And it's just some not so shocking things, but I'll illustrate here. This is in February 2008. That's when the phase 1A, which was purely northbound, this is when the construction began. And unsurprisingly, the crash frequency increases. And so on and so forth. In summer of that same year, the construction of the southbound lanes also ensued, and crashes rose. And so as construction ends in December 2008, there's a bit of a leveling off. The crashes don't decline, but perhaps people are getting more used to this construction. It's ending, the roads are being cleared up. And then finally, at the very end of this leveling off, the construction ends, and phase 1, both A and B are finished. However, as you notice, there is another jump after all this construction is all said and done. And what I was able to attest this to, with the best of my knowledge, is that this could possibly be a learning curve of some sort. There are a lot of visitors, a lot of travelers to Miami, especially the downtown parts. And so people perhaps may not be used to this. I know I've driven this lane when it opened, and I had no idea what I was doing, and I got stuck on the express lanes and had to take it all 7 miles before I had to backtrack. So it can be a little bit confusing. So there is a jump after all the construction is finished. But what makes me think this is a learning curve is that right after this large jump is a really large decline in crashes. And so this seemed to be good in that construction is finished, people are getting used to these express lanes, they're using them more knowledgeably, and there is a sharp drop-off in crashes after construction ends. I also note that phase 2 construction began on this drop-off in November 2011, but as I showed in the illustration, this phase was north of the segment that I analyzed, so I was just curious if perhaps maybe the construction on this phase maybe would bleed into the segment I analyzed and increase crashes, but it didn't seem to, at least on this most zoomed out perspective. So I did the zoomed out perspective. This is the most zoomed in perspective. I went ahead and did an aggregate analysis and a crash profile on a month-to-month basis. And as you can see, there are a lot more jumps and spikes and dips. And these are kind of reflecting the month-to-month changes that simply happen. And as much as one month may have an unusually high amount of crashes, the next month may have an unusually low amount of crashes. So ultimately, they usually do average out. But I just wanted to show kind of a month-to-month change. And though the trend might not be abundantly obvious, you can still kind of cut this graph down the middle and see a trend upward really towards the middle as construction is beginning and ending. And then it does kind of steadily decline on the latter half of this graph as well. So besides an unusual spike, which happens when phase 2 construction begins in the October-November area, I noticed there was an unusual quick spike in crashes during that time. And I really wasn't able to figure out necessarily what it is. But could it have been a bleeding down of the phase 2 construction into the segment I analyzed? Possibly. But as quickly as it came, it also quickly went away. And before and after this spike, you can see crashes are at a relatively low level. So the kind of comfortable medium that I arrived at was a 3-month aggregate mean. So we looked at the most zoomed in, the most zoomed out perspective. So this is kind of a comfortable medium in between, where the trends are a little bit more obvious, but again, you can still see more of the spikes that might happen on a month-to-month or seasonal basis. So again, I labeled the construction periods and when they began, and as to be expected, they increased when construction began, kind of leveled off as the northbound construction was ending, and then again peaked after all construction was finished. Again, possibly this learning curve theory where there was a short-lived increase in crashes, but then a sharp decline, implying that people got used to it and that ultimately this construction was a good idea and kind of returning to normal levels. And again, we see this kind of aberration in this spike in November, which again, I really couldn't figure out what it might be, but as I said, it was short-lived. And then what I did was I broke it up. Since the construction was, broken down into northbound and southbound construction, I wanted to look at the crash frequency strictly on the northbound and southbound express lanes. So what I found was, again, nothing entirely revealing. As construction started, you have an increase in the northbound lanes, which is what happened in phase 1A. But then, too, in phase 1B, when the southbound construction started, those crashes really don't have the same spikes the northbound did. So what I might attest this to is, why are people traveling to Miami? Well, in the morning they're likely coming to work, and in the afternoon they're probably leaving for work. So maybe this was a change in driver behavior during those peak periods, but it could be a number of different variables. But besides the northbound kind of outweighing the southbound in this period, they really mimicked each other, and when one spiked, the other one spiked too. So they were very similar, and they kind of followed the overall trend. And then my final analysis was just kind of looking at the crash types in particular. So rear ends and side swipes are the most common types of crashes, but especially because they were narrowing the general purpose lanes to accommodate for now 2 express lanes in each direction, I figured this extra sense of claustrophobia among drivers would increase, especially side swipes, not to mention rear ends. And we kind of do see that as construction starts, side swipes do increase, and as do rear ends, since those are the most common type of crashes pretty much across the board. So again, they all kind of followed similar trends. As the rear end spiked, so too the side swipes and the off-roads and all the other types of collisions. So they all did follow a very similar trend. So kind of just to tie it all together, the summary and conclusion is that this is an FDOT-funded research project with the ultimate goal of trying to implement crash predictive models into the Highway Safety Manual. And why? Because they're responsible for the planning and design of these roadways. So if they're able to now quantify safety and put that alongside the quantities that are yielded from operational and performance research, they can now have a better idea of which design elements to include in their managed lane facilities, whether or not to build these managed lane facilities at all, but it'll just better help them decide in designing and building these facilities. And so my particular contributions to this project were the literature review and the compilation of existing facilities. The literature review is still being undergone at Florida International University, and the existing facility compilation is ready for use. All of them are documented, so hopefully they can be easily compared and referenced whenever they may need it. And as far as I-95 Express goes, it's a relatively new facility. It started construction in 2008, or finished in 2008. It was an HOV facility in 1996, but from the data that I was able to extract as far back as 2006, still more data is needed. And analyzing facilities like I-95 Express over a longer period will kind of mitigate these increases that happen through construction, which are typical and not surprising. And so analyzing these facilities over the longer term will hopefully get a better picture of what's going on in the crash distributions and the crash frequencies so that we can more accurately develop these crash prediction equations and models. And so the idea here is, should these construction and transition periods that I analyzed in the I-95 be excluded? And the answer is yes, probably, because that's not the norm. When these managed facilities are operating over the long term, they're not going to be undergoing construction and having these construction-caused spikes in crash frequencies. However, that's not to say that these construction periods should not be analyzed further in another study, and perhaps we can use those over many facilities to develop maybe even crash prediction equations for facilities when they undergo construction, so that we know what to expect and what kind of spike in the crash frequencies will occur when they go under construction, and maybe perhaps mitigate them and lower them when we proceed with construction and save lives, hopefully. And ultimately, it's unclear the effect on safety simply because longer-term data is needed. But at the very least, just from the data that I analyzed from I-95, the crashes that occur before any construction and after are at the very least at kind of the same level. So at the very least, hopefully, safety isn't compromised and it's not degraded in any way. And hopefully, with the development of these equations and maybe getting to know managed lane facilities even more, we can even reduce crashes and improve the safety on these lanes. And that's really it. Yes.
I wonder if the databases that are this data from, do they have the data available in time of day?
Yes.
Yeah, I'm just curious.
Yeah.
Whether during peak time there are more crashes?
Yeah. So the question was the software that I use to extract this data. Can you get a kind of time of day or anything like that? And the answer is yes. It's extremely powerful. You can look at the crash reports themselves, see exactly at what time of day they happened, what direction you were traveling. The peak times, may vary from city to city and facility to facility, but yes, you can ultimately determine if it was a peak crash, an off-peak crash. It's a very detailed software and extremely useful. So
who could use the software?
Who can use the software?
Who could use it?
It's actually produced, I believe, here at the university.
Urban planning, geoplan.
Yeah.
Okay. So that contains all the facilities in the state? Or?
Yeah, as far as I could see, the question was the Signal 4 analytics software, can you analyze any facility in the state? And the answer is yes, you can zoom in and use an interactive graph to zoom into any facility, any roadway, any segment that you desire in the state and extract data. I could go as far back as early 2006, I believe is when the data started. But anywhere after that, they're continuing to update on a daily basis. So certainly very useful to me.
But you didn't analyze the time of day.
I did a peak and off-peak analysis.
Yeah, so
what did I find? There was nothing really necessarily shocking about it. It kind of followed the typical trends. There was nothing that really jumped out at me.
They have more as they do.
Yes, right, exactly.
What was the location of the accident? Are they like more toward the entrance of the happening, like because of the rigging movements?
Yeah, so the question was the accidents that occurred on I-95 Express, where do they usually fall? Where do they fall as far as location-wise? And the answer is, from the ones that I looked at, yes, there's a problem that people are weaving actually within these plastic poles that they've used as a barrier on I-95. And so there is a lot of weaving. Enforcement is very difficult. Since they're flexible plastic poles, people, if they get stuck on it like I did, would just weave out and cause some more side swipes. So yes, that would happen. But definitely the most common, though, as the facility as a whole, were crashes occurring close to interchanges. That was definitely the highest volume. And by exit and entrance ramps as well. But like any arterial, the rear ends and side swipes were definitely still the most common on the facility.
I have one more question. I'm not that familiar with this area, but the model that they use to predict the number of crashes, like what are some of the inputs, and can it be used to say predict the crashes based on the data to compare with the data that you showed?
Right. So the question was the prediction models, the equations that are used, what exactly are the inputs and the variables? And the answer is just from what I know, it's often to do with traffic volumes just to start. It can be a function initially of the traffic volume as a total, and then things like the lighting condition and things like additional little variables like that and characteristics. Perhaps as these are getting developed, things like the length of the segment might be a consideration, the width of the lanes, how many managed lanes there are, the type of barrier that separates the managed lanes and the general purpose lanes. All of these are definitely potential, I think, inputs that would affect crash frequency.
So if you use the model, probably way off when you compare to the actual data from I-95.
Right. Right. So hopefully, I mean, the construction is a short-lived thing, so that should perhaps maybe be excluded as to not skew the data or give an improperly high crash frequency when that's really not going to be the norm when these facilities are operating. So, all right. Well, thank you very much.
Inez,
Yes.
are you able to hear us?
Yes. Can you hear me?
So yeah. So I think if you can probably turn it over to Amara's. I think we are done with the 3 presentations from here. So I think it would now be Amara's and then Bruton.
Go ahead, Amaria.
All right. All right. Okay. My name is Amaury Ramirez, and I'm actually doing my internship at the International University of Florida under the supervision of Dr. Yang, Dr. Hari, and Mr. Peihu. During my internship program, I have been working with travel time reliability and how to set up analysis models to be able to estimate the travel time reliability. But first, I would like to start by defining what is travel time reliability. Well, travel time reliability quantifies the consistency or the variation of the travel time among a period of time of the day. And there is actually 2 general types of travel time reliability. One, we can do it by taking into account if the travelers are getting to the destination on time or if the travelers are getting to the destination with some kind of delay. The other one is by taking into account and tracking the variability of time that the travelers are taking to get from one point to another. There are actually some factors that influence travel time reliability, and one of them is the traffic fluctuation demand. Because of that variation of volume daily, some days have higher volume than others, and we are expected those days to have a higher congestion, which leads to a higher demand. We also take into account the weather condition, especially when the visibility is low due to precipitation because of the rain, or the precipitation due to snow or smoke, because the drivers tend to slow their speed and increase the headway distance between each other. We also take into account the actual geometry of the facility, like number of lanes, the width of the lanes, the width of the shoulders, and how many on-ramp and off-ramp lanes do we have. Sometimes in the facility we might have a work zone, and together with the work zone we might have a shoulder closure, 1, 2, or even 3 lanes closure, which leads to a decrease in the capacity of the segment. And the same effect happens when we have a traffic incident in the segment. Well, what is the actual problem? What do we need travel time reliability? Let me start by saying that traffic congestion is in our daily life, and drivers right now are getting used to it. Even though we don't like it, we are getting used to it, and we're planning for that delay. But what bothers drivers the most is the unexpected congestion. For example, when they know that they take 20 minutes to get from one place to another, and they plan ahead, and they plan that they're going to take 30 minutes, including the congestion that they expected. But actually, when they get to the facility or to the roadway, they find out that they're going to take an hour, and they get late for the destination. That is what frustrates the drivers the most, and that influences their expectation about the roadway performance and how, when, and where they're going to travel the next time. And those are the days that the drivers remember the most. I think that what the drivers really want is a consistency in the travel time, where if they take 30 minutes today to get to the destination, they are expecting to take the same 30 minutes tomorrow and the same 30 minutes next week, and so on and so forth. So what are some of the benefits that we can get from measuring travel time reliability? Well, one of the benefits is the reduction of the variation and the total congestion experienced by the travelers. Another one is that the freight carriers might increase the on-time delivery, which decrease the budget for the inventory, which tends to decrease the prices of the products, which is something that we all want. Also, the travelers will have more information about the trip they're about to make, and we are going to be able to reduce the vehicle emission and the fuel usage, because we're going to have less traffic, less vehicles stuck in traffic. We're going to spend less fuel and less vehicle emissions. Also, it is important for the engineers and the operators of the roads, because they will have all this information, and they're going to be able to track the performance of the roadways throughout the year, or in a day, in a month, and they're going to have all this information in hand, so they can play with it and try to improve the performance of the roadway. Some of the measurements that we use for travel time reliability are still in a developing process, but I'm going to mention 3 of them that are working really, really well until now. And one of them is the 90 to 95% of travel time, which estimates how bad the delay is going to be when we have the worst traffic condition. We also have the buffer index, which estimates how many minutes or how long do the driver have to add to the regular travel time to get to the destination on time. For example, if we have a 40% of buffer index and the regular time we take to get from one destination to another is 20 minutes, we take the 40% from the 20 minutes and we add it to the regular travel time, and that's the total time that the driver is going to need to get to the destination on time. Also, we got the planning time index. The planning time index estimates the total travel time that the drivers are going to take to get to the destination. For example, if we have a 1.6 planning time index and we usually take 15 minutes to get to our destination, we multiply that 1.6 by the 15 minutes, and then we're going to get all the amount of time that we're going to spend in the roadway to be able to get to the destination on time. Some of the tools that we use to help us with the calculation of the travel time reliability are, the first one is called FreeBot-RL. FreeBot-RL is a computational engine that uses Microsoft Excel basis and the methodologies of the Highway Capacity Manual 2010. Together with the FreeBot-RL, we also use the FreeBot Scenario Generator, which helps us to create all the possible scenarios that we might have in the roadway, including the combination of the weather probability, the incidence probability, and the and the vehicle demand fluctuation. For our analysis, we choose to analyze the corridor of I-95, which extends from Northwest 6th Street to the northwest of 125th Street, which is about 7 miles. And we actually decided to work with this corridor because it is one of the most congested and most unreliable corridors that we have in Miami. But we are also working and progressing well in the State Road 826. And the future goal for the project is to be able to apply the same methodology to all the corridors of the state. Well, to be able to calculate travel time reliability using FreeBot-RL, we need to follow 5 simple steps. And the first one is to introduce or input the project summary. Into the project summary, what we have to input is the name of the project, the name of the analyst, and the date of the analysis. And then we can go ahead and follow the second step, which is the creation of the seed file. The first step in the creation of the seed file, we have to input some important information like the starting period, the starting time, and the ending time of the period of analysis, which in our case was from 2 p.m. to 7 p.m., the started date and the ending date of the period of analysis, which in our case was a whole year, the 2012, from January 1st to December 31st. Another information that we have to input in this step is the number of segments that we're going to be working with, which in our case was 23 segments, and the type of terrain that we're going to be working on. And as we know, Miami is a level terrain. After we press OK, we have created the seed file in an Excel worksheet that allows to input geometrical information and traffic information. But first, we're going to start by inputting the geometrical information. To be able to input the geometrical information, we first have to define the segments using the visual word of Google Earth to help us visualize the actual corridor. And we have 5 choices. The first one is the segment can be on ramp, off ramp, waving, or overlapping. And if we don't have none of these characteristics in the actual segment, the segment is categorized as being a basic segment, which is the 5th one that I didn't show there. And all these segments are defined using the convention of the Highway Capacity Manual 2010. But we have also to input some other geometrical information using Google Earth, which is the number of lanes, the measure of the segment, the measurement or the length of the acceleration and deceleration lane, and the number of off-ramp and on-ramp lanes that we have. In the same worksheet, we have to input some other important information about the traffic, and those information are the free flow speed, the segment demand, the truck and recreational vehicles percentage, and some other adjustment factors to be able to get accurate results. After we input that information, we are able to go to the next step, which is the scenario generator. And the first step in the scenario generator is to input the daily demand multiplier. This value, the daily demand multiplier means compares one particular day of a particular month with the annual average daily value. And how do we calculate it? I'm going to put an example using the Mondays of January. We first use the annual average daily demand volume, but if we don't have that information, we can use a date that represents the annual average daily volume, which in our case was January 3rd, because that date we didn't have any incidents and the weather was good. And that, in our consideration, represents a good annual average daily volume. Then we take the average of all the Mondays of January, and we divide that average by the standard day we're choosing in the first step, and this is how we get the daily demand pattern. The second step in the scenario generator is the demand pattern configuration. In this step, what we do is basically to combine the date and the month that have a similar volume demand pattern or volume behavior And the way we do it is by pressing edit demand pattern first, and this rectangle is going to come up. And if we look at the left part of the screen, there we are defining the day of the week. If all the days of the week have a similar demand pattern, we're going to assign a number 1 for all the days from Monday to Friday. But in our case, in our analysis, we find out that Mondays have a different demand pattern than any other day, and that's why we only assign a number 1 for Monday. Then we find out that Tuesdays, Wednesdays, and Thursdays have a similar demand pattern, a similar demand behavior, and that's why we assign a number 2 for Tuesday, Wednesdays, and Thursdays. And similarly for Friday, we find out that Friday has a unique demand pattern, and that's how we assign a number 3 for Friday. And the same methodology is applied for the month of the year. And that's how we get the demand pattern configuration. Then the next step is to input the weather probability into the worksheet, into the scenario generator. And here we got 2 options. The first option is to use the default values, which are based on 10 years of data, which is really good. But in our case, we didn't use the default because we got enough data to calculate our own probability using real world information, and we input all the probabilities into the worksheet. Similarly, into the second step, in which we have to calculate the probabilities of the incidents and the probabilities that there will be a shoulder closure, 1 lane or 2 lanes or 3 lanes will be closed. And we also can use the default, which has pretty good information. But in our case, again, we calculated the probabilities by hand because we got all the information necessary for the probabilities. The probability that there will be no incident, the probability that there will be 1 lane closure, 2 lanes, 3 lanes, and so on and so forth. For the demand pattern, and remember that we choose the demand pattern in the previous step below, where we have defined the Mondays to Fridays and the days in the month of the year. Then in the next step is just, we don't have to input any information, but we are able to see the details of all the scenarios that we have created using the previous steps. And in our case, we can see that we have created 460 scenarios that we have to run in the next step. The running of these scenarios take a few hours. The whole process takes a few hours. But after the few hours, we are able to see some of the results. I'm not able to provide that much details about the results because we are in the process of analyzing them still. We are doing that. We are doing this week. But these are some of the results that we are getting until now. These are the travel time index, some statistics about the travel time index, and some other travel time index reliability. And in this picture right here, I mentioned the 95 percentile, which we can see that I have a number 2 there. That means that it will take double the average travel time to get from one destination to another. If we have a number 3, it will take a triple the time of the normal travel time that we take in a corridor to get from one destination to another. And this is a summary of what I have talked about. Travel time reliability measures the extent of the unexpected delays, and to be able to calculate these reliability problems, we are using FreeBall-RL, which is a computational engine that uses Microsoft Excel bases and the methodologies of the Highway Capacity Manual, and we can calculate the travel time reliability using 5 simple steps. Right now, we are still working in the I-95 and in the State Road A26, and the future goal of the project is to be able to implement those methodologies into all the corridors of the state. And I would like to give special thanks to Dr. Siva, Dr. Mohammed Hadi, and Dr. Yan because of the opportunity that they have given me for being here today. Thank you all. Hello?
Okay.
What's the name? Inez?
Yeah, any questions for Amaris? Either here. Okay, I can relay. You can come here and. Yeah, thank you.
Hi, can you hear me?
Yes.
Uh, the analysis period, I'd like to ask something about the analysis period. You said it's 1 year, right?
Yes.
Is there any chance that we can do it for a year back and a year forward, like, predictions or something like that?
I think you can choose any year that you like, as long as you have all the information about that year, like the weather probabilities, the incident probabilities, the demands, and all that. As long as you have all the information, I think you can do it for any year that you want.
I'm asking about the maximum analysis period.
Oh, it's 55 periods of 15 minutes. So the maximum that you can analyze in one.
You said no, the year, you said 1 year, right? The analysis period you have done for.
Yes, my analysis period was 1 year.
So can we do it for 2 years or 3 years, something like that?
I think as long as you have all the information, you can do as much as 10 years together.
Thanks.
You're welcome.
Any other questions here? Okay, if there are no other questions, I guess then we can move on to our last speaker. So Ines, can you transfer controls?
Okay, she's got it.
Hello, can you guys hear me?
Sure.
Can you hear me?
Yes.
Okay, perfect. All right, well, hello, my name is Brittany Hammett, and I was an intern at NC State working for the Transportation Research and Education, which we call ITRI, through the STRIDE program. And at ITRI, I worked with the Highways group. A little bit more information about myself. I grew up most of my life in Arizona, and a few years ago I moved to Wyoming to attend the University of Wyoming. And in Wyoming, I'm a junior in civil engineering with a concentration in transportation. I've interned with the Arizona Department of Transportation for 2 summers. The first summer I worked in materials testing as a technician, and I primarily tested asphalt. And the second summer I worked in construction, inspecting most aspects of bridge construction. So I have had some experience in the transportation industry, but before the summer I had never been exposed to the research component of transportation. So the purpose of this presentation is to show you and give you an overview of the work I've completed and the many things I've learned in my experience while working at ITRI in North Carolina. So my primary focus this summer has been working on the retaining wall asset management project for the North Carolina Department of Transportation. A simple definition of asset management is the use of a database containing an inventory and condition assessment of assets in order to provide quality to the assets as a whole and efficiency in the planning and budgeting for repairs and replacement of that asset. So that's a lot of words to say that asset management is simply a program that agencies implement that allows them to keep track of their assets and instigate the timely repair and replacement of those assets. So the intent of this project is to provide NCDOT with the tools to inventory and assess their retaining walls so that NCDOT is able to facilitate the timely repair and placement of retaining walls and prevent the wall failure. So in order to do this, the first step our research team went through was to identify wall characteristics. The second was to determine what data needed to be collected, conduct wall condition assessments, create a rating system, and provide an implementation strategy. So the purpose of this project is not only to come up with a great program that we can provide NCDOT, but our goal is to also outline an implementation strategy that will allow NCDOT to implement this program into their existing asset management program. So this project is not actually set to start until next month. So my role for the project was to simply provide the research team with a footing to begin their research and steps to complete the project. So my main goal was to outline all of the literature that I could find and the existing state of practice. And so what I first started with was looking at the different types of retaining walls. And what I determined was that there's basically two categories of retaining walls. There's cut walls and there's fill walls. And as you can see from this table that I created, there are different types of walls that go into each of these categories. So what I was able to do was create diagrams, as you can see here, of how each of these walls were constructed. And then I determined what materials were used in the facing elements and what materials were used in the reinforcements. I determined how these reinforcements were loaded and looked at load diagrams and other such diagrams that just gave me a better understanding of how these walls worked. And again, I looked at the construction of the retaining walls. And these, I was actually able to go to the construction site of a couple of the walls and was able to take these pictures, which I'll show some more pictures later. After I got a good understanding of how the retaining walls were built and how they worked, I was able to start looking at the existing state of practice. So one of the best resources we had was the National Park Service, which was working with the Federal Highways Association. And basically what I was able to do was outline the process that each of these agencies went through in order to rate or determine what should happen to each of these retaining walls. So I went through and was able to do that with a couple of different agencies, and this gave us an idea of what our program would look like for NCDOT. And these are among the sources that I was able to utilize in my research. So as I had mentioned before, I was able to go on an on-site visit to two different types of retaining walls and meet with a geotechnical engineer from NCDOT. And not only did this provide a hands-on experience that made the load diagrams and words on a page and from all the lit review come to life, but it also gave more direction to the types of retaining walls that are actually found in the state of North Carolina, because the geotechnical engineer actually had a much better idea than the literature that I was able to find. So after going through many different retaining wall asset management programs, I was able to identify 6 main components that were included in each asset management program that would be included in our program as well. The first is a wall acceptance criteria. So which walls are included in the inventory system? Some agencies used the criteria of if it's 2 meters high, it's in, and if it's not 2 meters high, it's not in the system. Other agencies, such as the National Park Service, had qualifications for these walls, which included historical background and other such information. The second component was what inventory data was included. So this isn't the data about the actual condition of the wall. This is the locational data. This can include pictures and videos of the walls. It can include as-built drawings and construction plans. It has a very widespread of possibilities. So it was very interesting to see what other agencies have done and what inventory they've actually included in their database. Third, and probably the most important, is the condition assessment and the rating system. So how are these walls assessed, or how is the condition of these walls assessed? Are they using the new LiDAR technology, which will do a scan and give you a 3D image of the wall itself? Are they using a tilt meter that they can place on the face of the wall, or are they just doing a visual inspection? And then how are they rating these, rating the condition of these walls? how are they distinguishing between a wall that's tilted at a certain angle versus a wall that has a crack on it? And so this rating system is a way to quantitatively assess how much or how great the need is for replacement or repair of each wall. The fourth would be the wall inspection cycle. So how often are these walls inspected? Are different walls inspected at different times? Are different walls inspected more frequently than others? And so some of the agencies would have, every 6 months they would have an inspection by just a maintenance worker that would drive by and make sure there's nothing drastically wrong. And then every 2 years, a qualified inspector would go in and look the wall top to bottom, and that would be the major inspection for that wall. And then the physical database. So what software is used for this database? Some agencies have used Microsoft Excel, others have used Microsoft Access, and others have used their individual software that they've created. And finally, how have other agencies utilized their system? What benefits have they found from their system? And so what is their action or their performance assessment of their retaining wall asset management system? So this project, the retaining wall project, is only beginning, and so my work will hopefully help build a foundation for the research team to continue literature review. And can you guys hear me all right? I just want to make sure. This project is only beginning, and it will hopefully help build a foundation for the research team to continue the literature review and begin this process of creating the NCDOT's retaining wall asset management system. So another project that I worked on for the Highways group this summer was a nationally funded project which looked at the location of a crosswalk in proximity to a roundabout.
Britton?
Yeah?
We can hear you.
Okay, perfect. Thank you. All right, the purpose of this project is to determine the best location for a crosswalk near a roundabout that provides the most driver expectancy and tendency to yield. So this project is already well on its way to completion, and my role was simply to create a system for collecting the data. After a few trials and errors, I created a few Excel spreadsheets and a process for data collection that can be completed by 2 people, a pedestrian that will be walking across the street and a data collector who would be recording every time that the pedestrian crosses each lane. The data recorder is responsible for recording the action of every vehicle that crosses a crosswalk or that doesn't yield for the pedestrian, and the nearest upstream vehicle. So this Excel spreadsheet allows for the data collector to determine if the car upstream actively yielded, if there was a passive yield, if no yield occurred, if the car was too close to yield, or if there was a gap where the car was too far away for it to be counted as a yield. So that's how the data would be collected in the field. And then once imported into the computer, the Excel spreadsheet would calculate the different amounts of each kind of yield, and then it can all be analyzed in however way the research team decides to use the data. A part of my role in the project was to think of different ways to analyze the yield rates, which is very difficult because you have to take into account the gaps, and so when there's actually a need for the yield versus when people are too close to yield. So it was a very complicated process that's still in the making. So finally, now after 2 months of research and working at ITRI, I can say that without a doubt I've learned a lot about transportation and the opportunities in the transportation field. This internship not only provided me with the opportunity to learn about transportation research and work alongside distinguished engineers, researchers, and students, but has given me the opportunity to move across the country, live in Raleigh for 2 months, and experience a lifestyle that I had never experienced before. I had always considered myself pretty transportation savvy before arriving to Raleigh, but the truth was is that I had never been without a car since I turned 16, and so sure I knew that there were modes of public transportation, but I had never had the need to utilize them. And so this summer when I moved to Raleigh without a car, I learned to use the buses and the trains and all of other modes of transportation that we learn about in our classes but don't always get the chance to utilize. So I was able to travel using planes, trains, automobiles, buses, boats, metro system, bikes, and of course I walked everywhere. And so this experience has taught me more about transportation than I could ever have learned by attending classes and staying in my comfort zone. So I've truly enjoyed my time here in North Carolina working with the ITRI Highways Group, and I would really like to extend my thanks to the STRIDE program at the University of Florida and to Daniel, Jeff, and the rest of the Highways team members for making this experience very meaningful, educational, and unforgettable. So thank you very much.
Thank you, Brittany.
Any questions? Anyone? Any questions for Britton? No? It's almost lunchtime. Is that it? Okay, if there are no other questions, I just wanted to thank all the 5 speakers. I think it was very interesting presentations. Looks like I-95 in Florida is the most studied roadway segment in Florida or something like that. But anyway, just wanted to thank all of you. I think it's been a very good presentation.